pop up. Okay. All right. Fortunately, Don and Jay couldn't be here today, but that gives me the opportunity to step behind the mic once again. So I'm really glad to welcome you, Bryan, Zhou, to the last NL seminar meeting of the, I think, calendar year of the semester for sure. Bryan's a second-year PhD student at UCLA. He's co-advised by Nanyun Peng and Kai-Wei Chang. And his research focuses on multimodality vision language work and embodied learning. He is also a part-time research scientist intern in the Segment Anything team at Meta Superintelligence Labs prior to his PhD. Bryan was a visiting researcher at Stanford SVL, working with Professor Jiajun Wu and Professor Fei-Fei Li. He has organized a workshop on Foundation Models and Embodied Agents at CVPR 2025 and the Embodied Agent Interface Challenge at NeurIPS 2025. His work has led him to receive the Best Paper Award at the SoCal NLP Symposium 2024. I usually like to relate some personal anecdotes I don't know you too well, unfortunately. So this was largely, I think, from your website. But anyway, I'm really glad to have you and really thrilled to learn about what you're going to talk to us about today. So with no further ado, please take it away, Bryan.
Thank you for the kind. Very, very happy to be here, and it's very nice to meet you all. And so a little bit about me before we start. So my name is Bryan. I'm a second-year PhD student at UCLA, advised by Nanyun and Kai-Wei, and work on multimodal grounded reasoning as well as visual embodied agents. So about today's talk. So I'm not sure whether you have seen the title abstract of the talk, but it's mostly going to be on based on my earlier work collaborating with Stanford on benchmarking LLMs and VLMs for embodied decision making and cognitive perception and reasoning. So before we jump into the papers, I want to give a little bit of background because I think maybe the topic is not exactly close to like what everyone here is working on. So I want to give a little bit of motivation on why we should care about the topic. So basically, autoregressive LLMs and VLMs, which most of us are familiar with, have been the most popular AI research topic. And another thing to know is that embodied agents and physical AI is probably the fastest growing, yet still infant AI research topic as of now. And right now, if you look at related works in this area, you can see that LLMs and VLMs are very widely used as either individual or trainable components for embodied agents. So either people are using them like in the SoCal paper as to perform certain functions or certain tasks, subtasks within the embodied agent, or they're using them as VLM component, like VLM or LLM components that are trainable and within the embodied agent framework, such as this paper, which is done by one of our lab members at NVIDIA. So yeah, this is a little bit of motivation on why we should care about the problem. So today, I want to share two papers with you guys. So the first paper is going to be this one called Embodied Agent Interface, benchmarking LLMs for embodied decision making. And just a little preview, the second paper, this paper is focusing on LLMs, the capability of LLMs, and which capabilities are important for embodied agents, and how are current LLMs faring. And the second paper is going to be about VLMs. So both of them are done with similar group of people, and we use the Stanford Behavior Challenge as our like data source among other simulators. So these are like the overarching theme of the two works is trying to form like the standard systematic definition of the capabilities of embodied agents, which are in LLMs and VLMs, and how we should understand them, and how are current LLMs, VLMs shaping up to it, and how do we improve them to be adequate for those purposes. Okay. So for the first work, let's start with a simple question. What is an embodied agent? So this is the first thing actually we asked ourselves when we started the project last year. So our co-author Jiajun shared a pretty, in my opinion, pretty good definition. So an embodied agent is like a robot that can perform many tasks across different environments. The highlight is two aspects: many tasks, which involve goals and decision making, and environments, which require interaction with physical spaces full of objects and states. So in today's AI systems, most of the state-of-the-art LLMs need to be augmented with these two capabilities to build embodied agents, and the ability to interact with complex embodied environments, the ability to make decisions to achieve specific goals. So for example, right now it's coming close to Thanksgiving. One of the common tasks that you might ask an embodied agent to do is set up like your Thanksgiving meal. So if you see in this example, you can see that when we ask the LLM agent to generate action sequence or basically sub-goal sequences to set up a table, it will generate put the turkey on top of the table because it's like linguistically very common to say that. However, in the physical embodied states, in the physical embodied environment, the actual correct formulation of this action sequence is that you want to achieve the state that the plate is on top of the table and the turkey is on top of the plate. You don't want to eat the turkey off of the table. So things like this really trip up the LLMs and VLMs when you are using them, trying to use them as embodied agents or components of embodied agents. So it's like sort of a sneak peek into the motivation of our this paper. So, sorry. Okay, so it's still quite challenging for LLMs to do embodied decision making because it's hard to interact with different environments with multiple objects, complex spatial relationships, and oh, sorry, I think the slides are a little bit. Yeah. So, anyways, I'll turn one slide. Yeah. Okay. So it's quite challenging for LLMs to do embodied decision making because it's hard to interact with different environments of multiple objects, complex spatial relationships, and low-level object properties. So in this paper, when we're trying to formulate the idea for this paper, we looked at all different ways of how existing papers in robot learning and embodied agent try to use LLMs, and we categorized them into 4 different categories. Namely goal interpretation, action sequencing, subcode decomposition, and transition modeling. I'll go into each of these in much more detail later on, so no worries if you have questions about them right now. Okay, so the problem with these papers is that they use LLMs in all different kinds of ways, and they're scattered across different domains for different purposes with different input and output formats. So there's no common ground and no standardization of what kind of capabilities or what kind of input output formats the LLMs or VLMs need for embodied agents. Okay, so there's a big hurdle because there's no standardized framework, difficult to compare methods, share insights, and build on each other's work effectively. So one of the goals that we want to do is standardization. We want to make real progress by answering the critical questions. Where do LLMs fail and why? And how can we improve them to address these bottlenecks? And perhaps a more practical question, if you're trying to build an embodied agent, which LLM is best fit for your specific task? So basically these 3 points. And to address these, we introduced the Embodied Agent Interface, a framework designed to systematically evaluate LLMs for embodied decision-making. And the goal is to make it as easy to use as possible. So yeah, let me first try to define the standardization that we use. So we're basing it on the Markov decision process, MDP, which is crucial to ground our evaluation framework in this theoretical foundation. Since we care about decision making, we based our framework on this. And this is the most common framework that people use for reinforcement learning and embodied agents, robotics, etc. So for the agent itself, we care about whether the agent is able to handle goals, states, and actions. These involve several critical capabilities. First of all, the input is natural language instruction. So we want the agent to ground it to the environment, to the objects and their current states. The output should be planning sequences, which can take 2 forms. Either an action trajectory, which is a sequence of actions that the agent plans to execute, reflecting its ability to sequence actions, or a sequence of states that the agent expects to achieve, which shows how it decomposes a high-level goal into lower-level sub-goals. Yeah, and the last important part is the single step dynamics to predict the future state given the current state at a specific action. So this reflects the agent's understanding of the transition modeling. So basically, some people will call this world modeling. Okay, and yeah, so this acts as a universal bridge to bridge the LLMs to interact with diverse environments seamlessly. So,
can I ask you a quick question?
Sure.
You're just saying that these are all different approaches, right? Like you would like independently try to have a goal of do goal interpretation, and then you independently try to do sub-goal decomposition, with an RL framework. Is that they're like different objectives, right? Okay.
So let me think. So yeah, so in this work, this is mostly a benchmarking work. So we try to evaluate each of these capabilities. We don't do any form of training, but if there were training involved, most of the existing works, there's two different modes. So like I introduced in the beginning, so there are two types of ways to do this. One is they use LLMs or VLMs as components. So in that case, they're individually optimized, or sometimes they try to fit it within overall, like a single backprop to update all the models. So in that, these are two like competing paradigms. Yeah. Okay. So I'll try to introduce each of the components and modules. So for example, this is a task, put the bow tie into the basket. And in this case, for goal interpretation, the agent first checks the environment, explores the environment to see what is there. And if the bow tie is on the table, the goal becomes moving it, is on the table, the goal becomes moving it off the table. The agent also sees the basket in the environment. So the final state is the bow tie inside the basket. The symbolic goal enables the planner to create this step-by-step plan to execute in the environment. Yeah, so this is symbolic goal interpretation. And the second task that we want to do is the breaking down symbolic goals into sequence of sub-goals, which is sub-goal decomposition. Sub-goal decomposition and action sequencing are basically two competing paradigms that existing models use for planning. The similarity is that they all try to decompose a higher level task into lower level task. Whereas the difference is that whereas sub-goal tries to basically describe the environment states that change and describe, okay, the first sub-goal is to try to say, in this case, for this, what's the task of bottling fruits, the first sub-goal is trying to basically slice the strawberry and slice the peach. Okay, so in this case, we have why is the speaker no? Okay, but it's okay. I think I could just walk through this simply. Basically, when we have a sub-goal that we want to execute, we basically have the model generate what the sub-goal is, and we can use a simple BDDL or PDDL planner to achieve the high-level planning, and the low-level action policy is executed by low-level action models that can be specifically trained. So this is like a decomposed view of how it would work. And there are also joint views, but I think that will be discussed in later parts of the talk. Okay. Okay, so that's for sub-goal decomposition. The other part that we want to talk about is action sequencing, which I introduced a little bit earlier as being similar to sub-goal decomposition. But the goal is, instead of predicting sub-goal states that you want to achieve, you're trying to predict action sequences that you want to execute. So for example, in an environment where the strawberry is in the pan, the goal is to put it into, cook it, put it into jam and bottle it. So basically, we ask the LLM to generate action trajectory. And if this action trajectory runs into issues in the process, this triggers replanning because the action trajectory can no longer be executed in the environment, and replanning is triggered. And we ask the LLM to replan based on this current state that it is currently in. The updated plan might include grasping the pan, put it in the oven, and then heating the strawberry. Okay. So with this new plan, the strawberry can finally be cooked. Okay, so this is a brief explanation of action sequencing. And the last thing that we want to explain is transition modeling. It's one of the most exciting yet underexplored capabilities for embodied agents, which is to understand the common sense of actions like preconditions and post effects of each action so that we can model what kind of transitions would occur after, before and after each action is executed. Okay. So for example, to clean a stained ball, the preconditions are that the ball is stained and the brush is soaked and the agent is holding the brush. The post effect of cleaning makes the ball not stain anymore.
Is it like how is this done in practice? Like, is the prediction the new state of the object?
So basically, the input is the action and the current environment state. You need to predict what preconditions must be satisfied before this action can be taken. The LLM needs to predict this, and also what post effects would occur after this action has been taken. Yeah. So so after the preconditions and post effects for each action has been predicted by the LLM, we can easily feed this into a general purpose planner, which lots of robotics people try to train. And using this, we can find a valid action trajectory. So this is another mode of how we generate action sequences, is basically first predict the transition model and then use a general purpose planner to generate the action sequence. Okay. So these are the 4 components. I want to pause here to see if you guys have any questions about either of these components. And if there are, I can address them right now. Otherwise, I can move forward with the presentation. Okay. So with this interface formulation, we successfully standardize the modules and provide annotation resources for the full annotation of PDDL plans and LTL goals. So PDDL is basically programmable planning language that is used for robotic planning. Linear temporal logic, LTL, is basically how we specify object states and goal states. It's basically linear logic that are unary, binary, or defines the relationship between all of the objects and their states in the environment. Okay, so another challenge in standardization is understanding how each of the how the LTL state definitions and goal definitions are applied to the objects. So basically, for example, to bottle fruits, we could put a strawberry in jar 2 and the peach in jar 1, or swap them both to achieve the same goal. And we use linear temporal logic to represent goals as finite state machine, basically providing a clean Boolean function that captures alternative paths. And this ensures that all valid goal states are covered in our evaluation purposes. Okay. So another key challenge is to locate where it's wrong. We often talk about environment feedback. The real question is like, how fine-grained can we make this feedback to pinpoint like specific issues, specific errors that the model makes? And we always say that environments can provide feedback. This is kind of the reason why we choose to base our data collection on top of the behavior simulation benchmark and also the virtual home simulation benchmark. This is so that we can have privileged environment information that can give us specific feedback that can allow, one is for the best error categorization, and the second is if we want to use this resource as a training resource, we can also pretty straightforwardly do that. Okay, so I think maybe one of the easier ways to understand this is that we can first look at how LMs do on each of the tasks that we just described. So basically we evaluated, this was, keep in mind, this was done for NeurIPS last year. So some of the models might not be the most up to date, but we evaluated 18 models on 4 core abilities. For these open weight models, we can see that they do not perform well on planning tasks on the left, such as subgoal decomposition and action sequencing. But they show pretty good performance on state understanding tasks in the right, like goal interpretation and transition modeling. For closed source models, like at that time was GPT-4o, Claude, and Gemini, we can see that they gradually perform better on planning tasks. Okay. So the question is, with such analysis, we're able to use LLMs more selectively for specific tasks, and we can answer the question, which model is best for my specific task? So if we look at some of the decomposed results for each of the subtasks, we can see that reasoning models like OpenAI o1 does very much have like a significant performance gap with the other models in terms of the planning task, subgoal decomposition, and action sequencing. However, with this improvement comes a 10 times more inference cost on average. So for our tasks in the benchmark. And so this is kind of a trade-off that you want to make. So for a planning task like this, you might want to use these reasoning models to achieve better, generate better plans or generate better decomposed subgoals, but you will have to pay for inference cost. Okay. And for state understanding tasks such as goal interpretation and transition modeling, there isn't very much a significant performance difference between reasoning models and non-reasoning models. However, there is still a 10% reasoning cost that is implicit in the reasoning models, internal reasoning chain. So for researchers who are doing this kind of tasks, we would advise probably going with a non-reasoning model. Just the instruct version will give you the same effect with much lower cost. Okay.
So are you prompting, you're running all these experiments, right?
Yeah.
Are you prompting everything like exactly the same way?
Yes.
The idea?
Yeah.
And then like, are you accounting for cases where like, I don't know, some models may need to be prompted a little bit differently? They want their output in a different form or something like that?
Yeah.
So how do you deal with, are you just like?
Yeah, it's a very good question. So so in this paper, we follow the, I'm not sure if you guys are familiar with the holistic evaluation of language models, that paper by Percy from Stanford. So they basically argue this point, whether the user should fit to the model and try to optimize the best prompt for each model, or should we try to come up with a general prompt that is like basically intuitive to the users, like usable to the users, and we try to optimize the prompt on all of the models at once, and we try to find what is like a most reasonable prompt. So in this work, we opt for the second option, which is we try to use one general prompt. So I think in the robotics community, I think their prompts are usually more on the simpler side. So basically providing the environment states, so depending on the task, you might want to provide the environment states, the agent states, and also the environment information and the goal in basically several chunks of the prompt. And we have done some prompt optimization on this, but I think in general, we found like a prompt that generally works roughly like pretty good for all the models, and we use that.
And each of you, forgive me if you said this and clearly and I just zoned, but each of the sub kind of steps that you're talking about here, subcomponents, the label space is like precise and well-defined, predefined, et cetera?
Yeah. So for different tasks, the evaluation is different, which I will cover in a bit, but just to let you guys know. So for Go interpretation, there's like pretty well-defined ground truths, basically just by accessing the privileged information in the environment at that time spent. But for transition modeling, subgoal decomposition, and action sequencing, we basically have the model generate these action sequences, or for transition modeling, we generate the pre and post conditions and use the planner to generate the sequences. But either way, the sequences are fed into the environment and executed. So at evaluation time, there's a simulation environment running in the background. And basically, we get feedback from the environment saying, okay, did this action sequence or subgoal decomposed action sequence successfully lead us to the final output to achieve the desirable result or not? Or in the middle, like we can have breakdown evaluation, which I'll talk about in a bit, which is like you get environment feedback for why you failed and what's preventing the execution of this action or something like that.
Are you going to distinguish between like syntax error and reasoning error?
Yeah, we do have sort of this breakdown. Yeah. Okay. So yeah, exactly for just like you mentioned. So this is a good segue to this part. There are we break down the errors into two types: goal-related errors and trajectory-related errors. So for goal-related errors, we have goal prediction errors for goal interpretation, and we have goal grammar errors like for basically action sequencing and sub-goal decomposition. And also we can break down the goal prediction errors further into false positives, missing goals, format errors, and hallucination. Format errors and hallucination are goal grammar errors. But I think you can see a pretty clear flow chart from like goal interpretation produces like goal prediction errors and grammar errors, whereas action sequencing and sub-goal decomposition can also produce these kind of goal errors. Whereas for trajectory errors, okay, maybe I should explain this a little bit. So I think it's in previous, like, especially robotic papers, they try to say like, maybe language models are not suitable for embodied agents because hallucination is a bottleneck. But in our benchmark, we actually find that surprisingly, there isn't actually a lot of hallucinations. The major bottleneck is still about complicated objects and their relationships. So I think as language models get better, the error distribution might change, but this is, as of last year, this was still the case.
I have a question though.
Yeah.
Maybe a little bit of pushback on that. Like, I mean, you could, I guess if false positives means like it's the wrong goal, right? Like you can say that's not a hallucination, but you can also cast it as a hallucination, right?
Yeah, exactly.
So I think it's tough. Like, if you interpret it that way, then 25%. That is the bottleneck because that's the major cause of false positives.
Right.
I think it's tough to frame as just separate from hallucination.
Yeah, exactly. I fully agree with your point. So the word hallucination is obviously overloaded and not well defined. So hallucination here, I think this is sort of position this paper for like robotics people. So they would, in their definition, hallucination mostly means like non-existent objects or non-existent states or things like that. So they call that hallucination, but for NLP people, we would probably understand, like, say, false positives also as a form of hallucination. So in terms of like robotics people, they try to frame false positives as this kind of like, say, this goal that doesn't need to be achieved, but the language model adds this certain goal to the problem. So yeah, it depends on your interpretation, but both are valid in my opinion. And in terms of trajectory evaluation, we have runtime errors, which accounts for the vast majority of our errors. Basically, at the runtime, we run into some execution errors. And basically, if a certain, say, like in the previous examples, I think I show like the strawberries is not in the pan and you want to put them in the oven and it doesn't work. Or if the chicken is on top of, like, you put the chicken on top of the table, which is something that will not trigger a runtime error immediately, but will trigger a runtime error later on. And there are a small percentage of trajectory grammar errors. I think that's less common. So yeah, we also had this is also automatically generated. So after the model generates a prediction for each of these tasks, the simulator automatically classifies them into, say, additional step, missing step, affordance error, wrong order, format errors, and hallucination. Okay, so this is just to help better understand what kind of errors there are. And if you want to use them as like reward signals for training models, this is also useful. Okay, so we propose to obtain fine-grained error messages by interacting with the environment. So take the example of reading a book. For example, if you want to open a chair, the environment provides precise feedback that the chair cannot be opened. This is a pretty extreme example, but in other cases, this does occur. In our observation, like the robot tries to open a water tap or something, in many cases. Okay. So there are different types of errors, and the next types of error, the different types of temporal ordering errors can also be identified through environment feedback. For example, if the precondition is not satisfied currently, but has been satisfied in the historical states, then it's wrong order, like sitting down before grabbing a book when you're trying to read. And if the precondition has never been satisfied, then it's a missing step. Like before grabbing the book, the agent should first find the book, like being in physical proximity of the book. Finally, it is the post effect. If the post effect has already been satisfied, it flags an additional step warning saying that this action is not necessary because the post effect of this action has already been satisfied. Good. So most importantly, I want to emphasize that the major innovation here, I think, for other researchers is that we package this into a very neatly packed environment. And you can actually run the whole evaluation on your LLM with a single line of code. As long as you have a LLM inference, you put the inference function in a designated area and you call this line of code, and you will be able to get a holistic evaluation of your language model performance on the embodied agent tasks according to our benchmark. Yeah, so this is for this paper, and welcome any questions and anything before we move on to the next one.
So I'm guessing like the fine-grained feedback you mentioned could be used for some RL or I guess back to your previous slide, like I'm wondering if you fail the preconditions, like what do you think the expected behavior should be? Like should it go back to the model that needs to identify the state transitions or the transitions? Is that kind of what you think should happen, like this feedback loop? And have you guys experimented with that, or maybe you're talking about the next paper?
Yeah. So for that, I think it depends on the task. So if your task is, say, action sequencing, then if the precondition is not met, then it's actually a natural replanning. So basically, the agent will get this environment feedback saying, I mean, physically, the agent will get feedback because it doesn't work, like the robot arm gripper will run into something or something like that. But in the simulation sense, we will get a more fine-grained reward saying that, okay, this precondition is not met. So that can be a form of reward, definitely. And for other tasks, it's less straightforward. For example, for transition modeling, if the planner runs into an error, so the planner will actually exhaustively try all kinds of action sequences and try to find one that works and before executing. So based on the preconditions and post effects that you have defined. So in that case, if the planner is unable to find a valid sequence, that would be, say, basically telling your model that your precondition or the transition models that you have defined are not good enough, or so it depends on the task, but definitely your point is valid. Yeah.
So it's interesting. This ontology really reminds me of like frame state, task-oriented dialogue, and all the kind of old-fashioned stuff from that we barely talk about anymore, where you want to figure out like slot identification and slot filling, things like that, right? You really want to figure out the intent, and like presumably it's just at this point maybe that's easier. We can just evaluate end to end. Did you figure out what the reservation was or something like that after having a conversation with somebody? And so we've just kind of like maybe moved the goalposts a bit, I guess, because our models are a little bit better. I'm wondering when or if you think, or what would have to happen for us to abandon this work?
Oh, yeah, exactly. So I think the major goal of this work is not saying that all of these tasks are like basically, you don't want to train a model specifically for any of these tasks. The point of this is that we find there are already existing a lot of works that evaluate basically on the overall success rate. They just care about overall success rate. But the problem with those works, in our opinion, is that they basically don't let you know which part is missing or which capability is lacking. So this basically helps you break down that evaluation into more fine-grained evaluation. So this is more like I would think of this like not a benchmark that people should like try to get the best scores on, but instead we're optimized too much to this. But it basically gives you a sense of if your model is failing like the overall goal, which capability is it actually lacking? Not that it's bad in the overall sense, but like which capability should you like focus more on? So this is more of an, I would say, an analysis benchmark.
But there's still the implication that it's going to then explicitly do each of these steps, right?
Not necessarily. So I think for this paper, we want to say like, so the evaluation is explicit, but I think the intuition, which is not covered in this paper, is that even if you were to adapt an LLM to like as part of the model, another bigger like vision language action model or something like that, you still need the kind of reasoning capability or the kind of thinking capability that it needs to like basically do each of these individual tasks, like understanding the goal, being able to generate actions, being able to understand the transition model between like one state and another state. So in that sense, we would hope that the models can have all of these capabilities together, but yeah, we still think that it's valuable to have an understanding of like which one you currently have and which one you currently do not have. Yeah, so yeah, I think maybe the next work will be a little bit more closer to the practical implementation. And yeah, the next work, because this is LLM only work, and the next work will be vision language model. And in that one, we will mostly be focusing on a couple components within the framework of what I mentioned. Okay. So before I continue to this, are there any other questions? Okay. So the second work is called ENACT, basically evaluating embodied cognition with world modeling of egocentric interaction. So this one is about using world modeling tasks to evaluate VLMs and to see whether if they show a sign of embodied cognition under egocentric interaction settings. So in cognitive science, there's a theory called embodied cognition. Essentially, this theory mainly argues that intelligence should arise from continuous sensory motor interactions with the world. And behind this theory, there are three important capabilities that contribute to embodied cognition, including spatial perception, physical interaction, and linguistic abstraction. So we know that VLMs are trained on internet-scale disembodied data. And in this paper, we're curious to answer the question, to what extent do VLMs emerge this embodied cognition from disembodied training settings? So previous benchmarks did evaluate each of these capabilities by isolating them one at a time. However, our work is the first to study these capabilities in synergy with an embodied world modeling setting. So since embodied cognition emphasizes sensory motor interactions with the world, building on these three abilities, the agent has to continuously know how its actions affect the environment and understand which actions lead to its current state. So this naturally leads us to frame the problem as a world modeling task. To explain the theoretical fundamentals for this work is that in egocentric interactions, the agent cannot fully perceive the complete state of the environment. So therefore, in this work, we adopt a partially observable Markov decision process. So we also used the behavior challenge, but this is a newer version. This is the behavior 1K challenge with a lot more tasks and a lot better rendering quality, basically because in this case, we want to have visual input to the VLM agent. Okay, so under the partially observable Markov decision process formulation, we treat the simulator scene graph as the environment state. and the RBG image that's rendered from the agent's egocentric point of view as the observation. And we define the action as the abstract symbolic difference between two consecutive states. So basically, the diff between two environment scene graphs would be defined as the action.
Is that a label, like the difference between the state graphs after an action? That could be discretely defined, right? Like, you know that if you turn on the faucet, the sink will be wet or something like that.
So basically we run the physics simulation and get the scene graph. So in this kind of like behavior simulator, under the hood, it's basically a physics simulator based on NVIDIA Omniverse. And so we define assets, we define robots, we define agents, but and also we define the starting states of each of the objects and how they're placed, what kind of temperature or whatever they're in. But as we run the simulation, basically in this case we run human demos that are collected based on, I think maybe this video will clear it up, but I just want to emphasize that as the human agent or the robot agent does each of these actions, perform each of these actions at each frame, the environment states, basically the scene graph will change. The scene graph consists of these things, basically unary states like the object's position, like position and rotation, also like temperature, all kinds of those variables. And also there are binary states like agents. If the agent is grasping something, there's a symbolic joint between the agent and the object. Also, whether two objects are touching, whether one object is on top of the other, inside the other, or these kind of relations. Like the simulator runs at 30 frames per second, and at each frame, the environment scene graph gets updated.
So like the ground truth is from the physics simulation.
Yeah, exactly.
Got it. Thanks.
Okay. So maybe it's easier to understand if I show a short video first of how the data is generated and collected in this kind of environment.
Like that's really high res, like reflections and everything. Wow.
Yeah, this is basically NVIDIA Omniverse quality. So with this is also the reason why we didn't release this paper last year, is because at that time the simulation quality still wasn't at this level. So there was a pretty significant real sim gap that we observed would affect the performance. And in this paper, we actually have some experiments on the real sim gap, because all of these environments are actually the environments in the Stanford Computer Science building. So basically they try to reconstruct this kind of environments and see if using the real environments versus using the simulator environments, there's a significant performance difference. And the result is that there's not that much. So given the high quality of the simulations right now.
That's pretty unusual though, right? Like usually there's quite a big gap.
Depending on the task. So in this case, maybe I should, it's hard to like rewind the video, but I can briefly explain. So there's basically two tasks that we're interested in. So basically one is forward world modeling and the other is inverse world modeling. So forward world modeling is basically given the current state and a sequence of actions that come after the state, what are the states that precede the actions. And the inverse world modeling is the other way around. We give the current state and the next sequence of states, and we ask the model what actions precede each of the states. Basically, we cast both of them as reordering problem, which I'll explain right now. So here's an example of how environment evolves when an agent interacts with it. So in state 0, the agent observes that it's holding a plate of pizza. And in the next action, the agent places the pizza into the refrigerator and observes the corresponding state scene. So here we only put like one state change per action, but in reality, they usually range in the number of tens to hundreds. So yeah, and then the next step, the agent decides to release the plate, perform the action, and observe the new scene. Finally, the agent closes the refrigerator door in its next action. And each of these actions are defined as environment state changes. Either a state is set to true or a state is set to false. And
sorry.
Yeah.
Is a state, the instantiation of a state is a representation of objects and where they are?
Where there are, so like there's unary states and binary states. Unary states such as position, and binary states such as relation. Basically, whether something A is inside B or.
Yeah, but it's at the relation level. It's abstract semantic representation.
Yeah.
Okay, great. And then, is O literally an image?
Yeah. Observation is RBG image.
Okay. So sorry. The state is known. The object in S0 and O0 are known. They're given, right?
Mm-hmm.
And then the action is, again, it's this relational thing. It's not like motor control or anything like that, right?
Yeah.
Okay. So this is all given in this abstraction. We're not telling a robot to do anything.
No. So in this case, basically all the data comes from replay data. So basically a human controlling a robot, remote teleoperation. That's how they collect the data. And after they collect data, we basically use that to generate our data set, which is we either on the, if we want to do forward world modeling, we basically give it the initial state and the actions, and we ask it to reorder. I'll talk about this in a second, but we ask it to reorder the images, basically the observations. Or if we give it the initial state and the observations, and we ask it to reorder the state changes, basically the actions.
Okay, but importantly, like the S0 to S1 given A0 is completely deterministic, right? There's no, there's nothing. Versus the SI to OI is completely stochastic. You just happen to have one instance of what O0 could look like or what O1 could look like, right? There's lots of ways a pizza can be on a table. There's lots of things that can also go. There's lots of camera angles. You just have one.
So in this case, basically, we already ran the
entire thing. And thus you have one.
Yeah.
Right.
Could be a different view that has the same action or the same effect on the states.
Yeah. Obviously, none of this are like one-to-one corresponding. There's like basically for each task we have multiple human demos, and each of the demos, the actions that the human takes is different, and also the camera view, like the position angles are different. So in that case, we would have several different kinds of simulations and several different streams, basically like this. And each of them is different. Some of them like would have like basically the same state change occurring, but the view is different.
Yeah. What is the minus versus plus?
Minus is like this state is set to false. Plus is this state is set to true.
So I guess why is action A1 set to false? Because like does that, like I'm just kind of trying to understand, like
robot ungrasps the plate.
Yeah. The robot basically puts the plate inside the fridge and releases it.
Oh, okay. So ungrasps, I guess, unopens or something. Okay. It's a negation of it.
Yeah.
Okay.
Okay. So we have this sequence of like state, observation, action, state, observation, action. There's also a reward in the middle if we want to do training, but in this case we're using static demos, so we have state, observation, action, iterations throughout. So since we use world modeling as a proxy for this agent environment interaction problem, we have to decide on how to evaluate VLMs. So as noted earlier, we asked whether VLM agents can continuously know how their actions affect the environment and which action led to the current state. So to this end, we introduced two tasks, forward world modeling and inverse world modeling, both cast as sequence or reordering. So forward world modeling is given the current observation and the agent's next actions. The model has to correctly order the shuffled next observations. Basically, the input is current observation, current sequence of actions, output, and also the shuffled environment states, environment observations in RGB images. All the blue ones are RGB image, and the yellow ones are scene graph. Okay, and the inverse is the opposite, basically giving a sequence of observations. The model must reorder the next actions that produce them. So so the way we design this is we don't use standard multiple choice QA because we want to sidestep the designer bias to create false positives. Instead, we just cast this as reordering questions. So there's no handcrafted distractors. So here's how we built the in-act dataset. We first obtain full robot trajectories via simulator replay, where each step contains the scene graph and the corresponding RGB frame. And then we segment the frames by abstract state changes. So for example, if we run the simulation and we observe at a certain timestamp several state changes that we define as like important, basically, for example, like grasping, or like something is inside of something, something on top of something becomes set to true or becomes set to false, we will keep that frame as a key frame. Otherwise, we skip the intermediate frames where no significant state change happens. So this is how we automatically extract the data from the human demos that are pre-recorded.
I guess in real life, like if LLM's doing this, there could be some behavior where it does something random and unrelated to the task.
Yeah.
But then eventually resumes to the right sequence.
Yeah.
So, but obviously your data is, humans will be perfect and they won't do any random stuff between their tasks, right?
There are imperfect. So we observe that things like the people, like some of the human controlled remote teleoperated robot would drop things on the floor and then pick them up.
I see.
Which results in a lot of different state changes. And we also take those into account.
Okay.
So as long as there are like meaningful state changes happening, for example, this thing becomes on top of the floor and out of my gripper, that is registered as a keyframe. Okay. So after we get this, we turn the segmented frames into multiple short trajectories of varying length and generate corresponding forward and inverse QA world modeling QA pairs. Okay. So here's basically two examples of forward and inverse QA. And we curated tasks from the behavior 1K challenge as our data source. So different tasks, you will have different observations and different action trajectories to form QA pairs. Okay. Just to give a very large table, don't need to look at the specific numbers. We evaluated 30 state-of-the-art VLM performances on human performances and also the human performances on forward and inverse modeling tasks. We can see that VLM performance drastically drops as the sequence length increase, while human performance holds relatively steady. So this highlights the current limitations of VLMs in multi-step long horizon embodied reasoning. And also another interesting fact is that we see VLMs consistently perform better on the inverse world modeling task compared to the forward world modeling task. This is because inverse world modeling is descriptive, whereas forward world modeling is generative. So for inverse world modeling, you basically, it's like a common VLM pipeline. Basically, you get all the information from the frames and you try to reorder the actions and reason in language space. However, for forward world modeling, it's much harder because you get all the information in terms of actions in language space, and you need to ground those actions in each of the images and try to reorder the images.
But in all cases, you're given the actions and the images. Just sometimes one of them is ordered, and sometimes the other one is ordered, right?
Yes.
And if you're able to convert the images into states, then it becomes fairly trivial to figure out the relative ordering of the unordered thing.
Yes.
So shouldn't it be the same task, basically?
So that assumes that you're always able to, let me think. So it's still different because one is trying to, given the action, predict what state changes, because you have unordered, but one is ordered, the other is unordered. But in the first case, you're trying to, given the actions that cause them, you try to predict the outcome, try to reorder the outcome.
Yeah, I understand that, but nevertheless, the actions between two states are deterministic given the states, and the state between two actions is also deterministic, right? The state given the state and action is also deterministic, right? If you give me a mapper from image to state, I think I could do both of your tasks equally well.
Yeah. Oh, I see your point now. So yeah, I think that's a valid point. So basically saying, if we can reliably translate all the states, basically all the images given observation, I can like have all the privileged environment information saying, okay, given this observation, I can clearly tell all the relations between each of the objects and all the states between each of the objects, which are sometimes like, basically they are numerical, like the positions or like the distances or how whether something is touching something, how far is something, whether something has been heated. So some of them are not directly observable from the image alone, because basically you're turning on the stove and the state changes, like something, the water becomes boiled, but the water is in the kettle, so you cannot directly see the water. So you have to infer that based on the action, not just by looking at the image. So it would be impossible to directly translate the image into all the states, because say if you're looking at a kettle, you cannot tell if the water inside is boiled or not boiled.
Yeah, I get that part, but it seems like you have that same problem no matter what order you're going in.
Let me think. So if you're saying like because if you have the actions, basically that's like if the actions are given, so you know all of these are true, that they happen in this order, the state changes happen in this order. But if you have the images as input, you don't really know, like if you have the images as order, you don't really know, like at each time step what the states necessarily are in this image. So you won't be able to basically directly map this image to a certain, like a very long list of states.
Take it up again in our one-on-one.
Yeah, I think, yeah, we can talk about more of that in the, offline. Okay, so.
This is without training, right?
Sir?
Without training, right?
Yeah, this is just the evaluation. Okay, so I'll speed this up a little bit. So I want to share the major findings here. I talked about them in a little bit. So the interaction length range from 3 to 10 steps. We can evaluate around like the open weight and proprietary VLMs, and we can see that we get a pretty symmetric distribution, whereas when we increase the number of steps or the sequence length, the performance drops very significantly for all the existing VLMs, whereas human performance holds very steady. And this human performance is collected using basically Amazon MTurk annotators. And also, we can see that consistently the forward world modeling task for VLMs is harder than the inverse world modeling task for VLMs, but for humans, the difficulty seems roughly on par. Okay, conclusions appeared. Okay. So also there are some other interesting takeaways that we get from this. We find that VLMs tend to make more errors with the left hand. So basically, when using the left gripper to grasp objects, there's more errors that we can see from there. There's suggesting an implicit right-handedness from the training data distribution that's affecting the VLMs. And we also find that VLM perform better on images with visual distributions similar to human perception. For example, performance drops when images are captured from a large aperture, fisheye lens, or like unusual viewing heights that differ from like human perspectives. Okay. Also, some of the features that do not really impact the performance that much are one, image realism, and the second is robot appearance or robot color. Okay, and we also provide an automated error analysis module, like in the previous paper, that performs stepwise error categorization given the model predictions. So this is evaluating errors directly from output permutations. Because this is directly evaluating errors from the output permutation is difficult and often uninformative. So about the underlying cognitive mistakes. So instead of directly evaluating that, our approach converts the model's output into a format that allows direct fine-grained comparison with the ground truth. So for forward modeling, world modeling, even when we're predicting images, we convert those images directly using privileged information into the environment states and use that for error analysis. And we can see from this error analysis on GPT-5, we can see the majority of the errors are either hallucination or omission of state changes in both cases. Okay, so this is a dataset viewer and basically shows how the data, like how the human annotator is actually doing the annotation. So human annotator is given this kind of information. So this is a very short one. It ranges from 3 to 10. So this is the shortest possible sequence it can have. And you will need to reorder those actions. This is full world modeling. And in inverse, you have the actions on top and you need to reorder the environment states.
Why would you give the annotator a chance to try again?
So this is this is on the website. So in practice, the annotator doesn't get to try again. Yeah. So basically, this is for the second work, and feel free to let me know if there are any questions.
Thank you.
Good.
I'm thinking that the inverse world modeling is just very similar in distribution to training, right? Like text captions are kind of sometimes they talk about the state of things, so it's like it's it's kind of implied in the pre-training, I guess.
Yeah, yeah, and also pre-training data, a lot of times you're asking it to generate actions.
Yeah.
Whereas for model modeling is for like I think this example Yamlet Quinn likes to use very much is like, imagine a cube floating in space. What happens when you rotate it 90 degrees?
Yeah.
Whereas for modeling is similar in the case that you execute these actions, what would happen to the environment?
Yeah. Much harder.
I think we're out of time for today. But thank you very much for attending these seminars over the semester, and hopefully see you in 2026. Stop.